Let's recall that when we were optimizing a function of one variable on the closed interval a, b, we'd do the following. First, we'd find and classify the critical points on the interior of the interval. Then, we would check the values of the critical points against the values that we found on the boundaries. Now, if we suppose that we're working with a function of n variables, the question becomes, how do we find extrema on sets with a boundary? For example, suppose that we wanted to find the extrema on this amorphous blob. We know how to handle the interior, right? We tackle the critical points as usual. But it's not clear what we do with the boundary. The reason is that the boundary might now have infinitely many points, and it's impossible to check all of them by hand. So we need something else, something called Lagrange multipliers. For this, we'll have two functions, f and g, and we'll work on the set S of all roots of g. If f achieves either a maximum or minimum on the set S, then there is some number called lambda, such that the gradient of f is equal to lambda times the gradient of g. That is to say, the gradient vectors for f and g must be parallel. Before jumping into an example, it's worth pointing a few things out. The first is this weird set S and what its relationship to g is. Since S should represent the boundary, if the boundary is described by an equation, we use that equation to define g. For example, if S was the unit circle, then the equation defining S is x squared plus y squared equals 1. This means that our function g is x squared plus y squared minus 1, so that S corresponds to the set of points where g is 0. Now sometimes, the theorem above is stated in a different way. Start by defining this function, called the Lagrangian, as shown. The theorem can then be restated by saying that if f achieves an extremum at c, there is some number lambda, such that c lambda is a critical point of the Lagrangian. And if you think about this for a while, you'll see that being a critical point of the Lagrangian is equivalent to the gradients being parallel and g being 0. Finally, we can also use Lagrange multipliers to solve constrained optimization problems, wherein we'll set g to be the constraint function. Okay, time to do an example. Let's find the maxima and minima of the function xy on the ellipse 4x squared plus 9y squared is 36. I'll start by drawing the set S, just so that we can see what it looks like. It's an ellipse whose major axis is the x-axis, with major radius 3 and minor radius 2. We define g as the function which defines our set like so, and compute the gradient of f and g. By the theorem of Lagrange multipliers, this means there's some number lambda such that the gradient of f is lambda times the gradient of g. If we set these to be equal, then that gives us the following two equations. Now from this we get two equations, but we have three unknowns. On the other hand, we also have the constraint, which I'll write here again just so we have it in mind. Now we need to solve these three equations for x and y. If we get lambda, great, but we really don't need it. We'll start by subbing 1 into 2 to get the following, which we can rearrange and factor like so. Thus, either y is equal to 0, or 144 lambda squared minus 1 is 0. So starting by assuming that y is 0, note that this in turn implies that x must be 0. But these must also satisfy the constraint, and they clearly don't. Thus, we reject this case out of hand. So then let's assume the other term is 0. Solving for lambda, we see that lambda is either plus 1/12 or negative 1/12. We'll start by assuming that it's positive 1/12 and plug it into equation 1 so that y is equal to 2/3 x. We then plug that into our constraint, which reduces to 36 is equal to 8x squared. Solving that gives us x is plus or minus 3 over root 2. Now we still have to find the y values, but since y is 2/3 x, we can plug x in to get plus or minus root 2. Thus we have two possible solutions as so. Next up, suppose that lambda is equal to negative 1/12. If we do exactly the same thing that we did above, that gives us negative 2/3 x, and that minus sign makes absolutely no difference to the constraint, so again we get 36 is 8x squared, and again that gives us that x is plus or minus 3 over the square root of 2. But this time, y is negative 2/3 x, giving us the same answer of plus or minus root 2, but with the opposite sign to whatever x is. That means that we have two more candidates with the exact same set of numbers, but this time they have opposing signs. Thus, there are 4 candidates in total. And since we have no way of testing which are the maxima and which are the minima, we just have to plug them back into our function. When the signs of x and y coincide, we get 3, while when they differ, we get negative 3. Hence, the first set of points in that top row give us the maxima, while the latter set of points correspond to the minima. So Lagrange multipliers are the tool that allow us to deal with the large boundary sets that can occur when dealing with higher dimensional domains.